In the last two lessons, we talked about sequential decay, transient and secular equilibrium. And in this lesson, we are going to learn how we can apply transient and secular equilibrium in practice. We're going to talk about radionuclide generators. But what is a radionuclide generator? Radionuclide generators are devices that make use of transient and secular equilibrium to ensure on-site and on-demand supply of radionuclides. How does a generator work? A radionuclide generator makes use of substrates such as aluminum oxide placed in a column on which the mother radionuclide will be deposited. The mother radionuclide usually adsorbs strongly on the material, and while adsorbed on the column, the mother radionuclide will generate decay to its daughter. The daughter isotope will then be removed from the column, also called elution, using appropriate solvent, such as for instance physiological solution, while the mother remains adsorbed on the column. Such a generator is only possible if mother and daughter will have different chemistry, so different adsorption affinity on the substrate at the elution conditions. When is the best time to elute the generator? In practice, the best time is at equilibrium, because that is when the maximum activity of the daughter will be obtained. That means that the best time of elution for transient equilibrium is if the time elapsed after the mother radionuclide was deposited or the time of last elution is equal to or more than 4 times the half-life of the daughter. For secular equilibrium, the most optimal time is 6 times the half-life of the daughter. Let's now have a look at some practical examples of radionuclide generators, starting with the molybdenum-99 technetium-99m generator, from which we will elute technetium-99m. Technetium-99m is the most often used radionuclide in medical diagnostics, accounting for 30 million examinations per year. This radioisotope is applied in diagnostics in many medical fields, cardiology, oncology, and others. You can see here an image of bone scintigraphy as an example of a diagnostic test to assess various bone conditions. Here you can see another example, this time of kidney cancer. The molybdenum technetium generator was for the first time prepared by Tucker, Richard, and Green. Except at that time they didn't have any idea what can be done with such a device. They had discovered that molybdenum can be separated from technetium and that elution can be carried out repeatedly. But what could you do with that? Little did they know that this generator will be the most often used one in the history of nuclear medicine. Molybdenum-99 technetium-99m generator is based on transient equilibrium. The half-life of molybdenum-99 is 66 hours and technetium-99m has 6 hours of half-life. This also means that this generator is best eluted each 24 hours, equal to 4 times the half-life of technetium-99m. But why is technetium-99m the most often applied radionuclide? First, it has a very suitable half-life of 6 hours, which allows obtaining a diagnostic scan without inducing unnecessary damage to the patient. Second, it emits a gamma of 140 keV, which is perfect for detection, allowing to obtain high-quality images. Third, technetium has extremely rich chemistry, which allows to prepare various radiopharmaceuticals, explaining its application in detection of so many medical conditions. Last, but definitely not least, technetium-99m is supplied by a generator, which allows its elution in the hospital, avoiding all supply and logistics issues, which would have tremendously hindered the application of such short-lived radionuclide. Let's now do a practical example. A hospital receives a technetium-99m generator at 8 o'clock in the morning. At this time, the activity of technetium-99m is 0. The activity of molybdenum-99 is 50 terabecquerel. Knowing the half-lives of both radionuclides, 66 hours for molybdenum-99 and 6 hours for technetium-99m, how much technetium-99m can be eluted at 2 o'clock in the afternoon? We should always start by checking whether at the time of elution equilibrium has been obtained, because if there is equilibrium, we can use the simplified equation we discussed last lesson. Now we know that the molybdenum-99 and technetium-99m have a transient relationship, so equilibrium will be achieved at 24 hours. But in our case, only 6 hours have elapsed since delivery of the generator. So because equilibrium has not been attained, we should use the whole equation that relates activity of the mother and daughter. We cannot make any simplifications. Next, we calculate the decay constants, like we have done before, which gives us the decay constant of molybdenum-99, which is 2.9 times 10 to the power of minus 6 per second. The decay constant of technetium-99m is 3.2 times 10 to the power of minus 5 per second. Now we fill in the decay constants in the equation of the activity, and we will fill in the 6 hours converted to seconds, which is 6 times 3600. We also fill in the activity, which is 50 terabecquerel, so that's 50 times 10 to the power of 12. And that results in 2.4 times 10 to the power of 13 becquerel of technetium-99m after 6 hours. Thank you for watching this lesson. And remember, when calculating activities in sequential decay, make sure that you first find out if equilibrium has been attained.